Hello everyone. Today we are going to talk about our third day of related rates, and today we're going to specifically talk about cones. So I have some different pictures of cones here just to refresh your mind as to what they are. At the bottom here you'll see just your traditional picture of your cone that you should remember from geometry, and you'll notice that we are talking about right circular cones, meaning that the altitude is perpendicular to the base. And of course we have a radius of our base. So those are the two important words that we're going to be using again and again through this video. Okay, so our first example says a paper cup, which is in the shape of a right circular cone. So I'm going to go ahead and draw that. So sort of like that. Is 16 centimeters deep. So 16 centimeters deep, and has a radius of 4 centimeters. So my radius there is 4. Water is poured into the cup at a constant rate of 2 centimeters cubed per second. So water is being poured in, okay, and they're giving us a rate. So right away our eyes should notice they're giving us a rate. That tells us they're giving us the derivative. Okay, and so what's the derivative of? Well, the unit of measure, 2 centimeters cubed per second, and the concept that we are filling something up should indicate to us that they are giving us the derivative of the volume, the rate of the volume. So dV dt is 2 centimeters cubed per second. Okay, so now if we read the next question, or part A, it says, at the instant that the depth is 5, what is the rate of change of the height? So you can see here what they're looking for, the rate of change of the height, that's dH dt. Okay, that's our unknown. But notice that they want it at the instant when the height, the depth, the height, is 5. So when h is 5, what does that mean? Well, you have this idea, this concept that you are filling up the water, okay, in the thing, and what it's saying is, what is the rate at which the height is changing when your height, okay, of the water is 5? Now, one thing that we've been asking ourselves a lot in the last couple videos is there a constant? Do I have anything that is constant? Well, if you look at these problems with the cones, generally there is none. And so let me talk about why that is. If you look at the water right now, okay, clearly the height is changing as we are pouring more water in. But if you look at the radius at different times, so here, if you look at the radius right now, it is so long. And then if you continue and fill it up just even a little bit more, what happens to the radius? Well, now the radius is just even that much longer. And so both the height and the radius are changing in a cone as you are filling it up or emptying it out. So we would have to say that there is not a constant. Okay, the next thing we need to talk about here is that there is this really important concept when we're dealing with cone problems where we have to look for a ratio. And the ratio that we have to build is radius to height. So we're always building the ratio of the radius to the height of a cone, of the original cone, before you start filling it up or anything else. So if you look at this cone that we have right here, so that's really important. You probably want to star that in your notebook, that you are using original values. So the original height and the original radius, okay? So if we look at what we were given originally, the size of the actual cup, okay? The cup was 16 meters deep, so a height of 16 and a radius of 4. So we would say the ratio of radius to height would be 4 to 16, which if I were to go ahead and simplify that, I could say it was 1/4. All right, now if I want to go ahead and cross multiply so I can solve for one variable in terms of the other, I would have h is equal to 4r. And that solves for height in terms of radius. I could also go ahead and solve for radius in terms of height by dividing by 4 on both sides. I'd have radius was equal to height over 4. And we want to go ahead and find both of those. Both of those are going to be very important to our problems depending upon what you're asked. And since we're asked two different things, part A and B, we are going to need both of these. So it's always a good idea, get your ratio. That's a must. You have to have a ratio for these problems. And then solve it for both variables, h in terms of r and r in terms of h. All right, so now let's go forward and work through this problem. Okay, so the first part of this problem asked us to find the rate at which the height is changing at the instant when the height is 5, at the instant when there's 5 centimeters of water in the cup. Okay, so if we're talking about, the only thing we know here is we're talking about volume. We're filling it up. So we're going to go ahead and grab the formula for volume of a cone. Okay, this is another formula that you are going to need to commit to memory. Volume of a right circular cone is 1/3 pi r squared times h. Okay, so we need to go ahead and memorize that. All right, now what you want to do with these problems is you only want one variable, which is why we had to use our ratio over here in order to get one of the variables in terms of the other. So in order to determine which variable we want to keep and which one we want to get rid of, we have to look at what we're solving for. If we're solving for dh dt, we want all h's in our formula. So we want to get rid of the r. And so to get rid of the r, I'm going to go ahead and look for a formula for r that uses h. And that, of course, is what I solved for earlier. So I'm going to write volume equals 1/3 pi. Instead of my r, I'm going to go ahead and put h over 4, and then squared, and then times your h that was already there. All right, so now we got to go ahead and clean this up. So volume is equal to 1/3 pi. When you square a fraction, of course, we square the top, h squared, and the bottom, 16, and then times h. Okay, at this point I'm going to go ahead and recognize that I have 1/3 and I have 1/16 that I can multiply. So volume is equal to 1/48 pi, and then I have h squared times h, which is h to the third. All right, now I am ready to go ahead and take the derivative of this with respect to time. Okay, so I can go ahead and do the derivative with respect to time of this equation. So I would get dv dt is equal to, all right, so 1/48 and pi we know are numbers. And so you're going to go ahead and take this 3 and multiply it times that. So 3 times 1/48 would simply be 3/48, then your pi, then h squared, and then dh dt. Okay, so I can go ahead and plug in what I know and clean up as I do. So I know dv dt is 2. Okay, 3/48, I'm going to just simplify to 1/16, and then pi. Now the h that we are using here, very important. The h we're using here, they wanted the rate of change of height here when h was 5, when the height is 5. So we're going to use that height of 5. So 5 squared times dh dt, because that's what we don't know. All right, so now we just have to solve this for dh dt. So if I clean this up a little bit, I would probably, actually what I would do at this point is, since I have 1/16 here and I want to get rid of that to the other side, I'm just going to multiply both sides by 16. So I'd have 32 equals, obviously pi times 5 squared would be 25 pi, and then dh dt. All right, so the next step would just be to solve for dh dt, and I do that by dividing by 25 pi. So I'd have 32 over 25 pi, and what is my units of measure here? That would be centimeters per second is equal to dh dt. And so the rate at which the height is changing would be 32 over 25 pi centimeters per second, or the height is increasing at the rate of, and so that's our answer. All right, so that's just part A. All right, so now we have to do the whole same thing with part B. But if we go back and look, all right, we're going to still use this same volume formula. But now, as we are approaching it, since we want the, at the instant the radius is 3, what's the rate of change of the radius? So now we want to take that formula, but we wanted everything in terms of r's. All right, so we're going to keep working on this problem here. All right, so now part B of this is saying what's dr dt when r equals 3. All right, so all of our other values are going to stay the same. So we're going to start off, like I said, by taking that volume formula. 1/3 pi r squared times h. Okay, but this time, instead of going ahead and replacing the r, I want to replace the h because I want to keep the r's. I want everything, all of my variables to be r in terms of r, since that's what I'm looking for over here. All right, so what was the formula for h? If you look back in your notes, h was equal to 4r. So when I replace it, I would have volume is equal to 1/3 pi r squared times 4r. All right, so if I clean that up, volume would be 1/3 times 4 is 4/3 pi r squared times r would be r to the third. All right, and so again, I want to take the derivative of that with respect to time. And so I'd have dv dt is equal to 4/3 times 3. So when I take that exponent and multiply it times the 4/3, I would just get 4. And then pi r squared dr dt. So I can plug in what I know. I know dv dt is 2. 4 pi. Remember, I want the radius at the instant that I'm if I want the dr dt, it's at a certain instant. And what is the radius at that instant? It's 3. So 3 squared times dr dt. Okay, so that makes 2 equal to 4 times 3 squared. Well, 3 squared is 9 times 4 is 36 pi dr dt. So I divide by 36 pi and I get 2 over 36 pi, which of course I could simplify to 1 over 18 pi, and that is my dr dt, so I'm going to go ahead and stick a unit of measure on that, centimeters per second equals dr dt. So the rate at which the radius is changing is 1 over 18 pi centimeters per second. Okay, let's take a look at our second question here. Water is being withdrawn from a conical reservoir 3 feet in radius and 10 feet deep. Okay, so we have a conical reservoir, okay, and that's 10 feet deep, and there is a 3-foot radius. And it's being withdrawn at a rate of 4 cubic feet per minute. So again, that's giving us the rate of change of volume. So dv dt is equal to. And if we notice that we're withdrawing it, that means that it is being taken out. That means it's decreasing. So our rate would be negative 4 feet cubed per minute. Okay. How fast is the surface falling when the depth of the water is 6 feet? So they want to know, how fast is the surface falling? Sounds like they're talking about the height falling. How fast is the height falling when the depth, when h is 6? All right, so remember we said the first thing we need to do with problems like this is get our ratio. Okay, so, and our ratio is always radius over height. So what is our radius here? Our radius is 3 and our height is 10. Remember, we're using the original dimensions of the cone. Okay, so nothing can be reduced with 3/10, so we'll just cross multiply. We get 3h equals 10r. Oops, that's supposed to be an r. All right, now, because if we look at what it is we are solving for, okay, we're going to be solving for height, everything we want in terms of h when we get to our formula. In that case, we're going to go ahead and solve for r in terms of h. All right, so if I do that, I can divide by 10, and so I get r is equal to 3h over 10. Now, if you're not sure, you can solve them both and then take a look and see which one you need. Okay, so this is the ratio that I'm going to go ahead and use once I need it in my formula. Okay, so speaking of that formula, let's go ahead and pull out the formula for volume. Volume is equal to 1/3 pi r squared h. And here's where because we're solving for dh dt, we want everything in terms of h. So I want to replace that r with my formula that I just found over there. Okay, so I'm going to go ahead and write this as volume is equal to 1/3 pi times 3h over 10 squared times h. All right, so that would be volume equals 1/3 pi times 9 over 100 and then h cubed. Okay, if I kind of pull the fraction away from the h there. And then that would be h squared times h. All right, so I can go ahead and divide this 3 in the bottom here into this 9. And so I'd be left with volume is equal to 3 over 100 pi h to the third. Okay, so that's my volume formula in terms of height. Okay, I'm ready to go ahead and take the derivative of that with respect to time. So I get dv dt is equal to, okay, so I'm multiplying 3 over 100 times that 3, the exponent of 3, and I get 9 over 100 pi h squared times dh dt. All right, so dv dt, of course I know, and so I can start plugging in what I know. That's -4 is equal to 9 over 100, then your pi, h squared. Well, my height at the time when I'm searching for the rate of change of the height is 6. So 6 squared would be 36, and then dh dt. Okay, so clearly I have to do some multiplying here. So kind of if I do a little scratch off to the side, 36 times 9, that's 54, carry the 5, 27, so that would be 32. So I can see here that I have -4 equals 324 over, and that should be pi, over 100 times dh dt. Okay, so one last step, of course, to go ahead and simplify this. To solve for dh dt, we would, in fact, be multiplying both sides by the reciprocal. So the best thing to do here to go ahead and solve for dh dt is to multiply both sides by the reciprocal of that fraction, which, of course, would be 100 over 324 pi. Okay, so when I do that, clearly on this side, those just go away, and so I get the dh dt. And on this side, well, I can go ahead and multiply, and that would be -400 over 324. But I also might note that I could go ahead and cancel this 4 into the 324. So 4 goes into 324. Well, let's see. 4 goes into 32 8 times, and 4 goes into 4 once. So 81 pi is the denominator, and -100 is the numerator. And of course, I need a unit of measure on that, and that would be feet per minute. So the rate at which my height is changing, the height is going down at a rate of 100 over 81 pi feet per minute when the height of the water is 6 feet. Okay, so the second part of this question is asking how fast is the area of the surface decreasing at this instant. So it's talking about finding how fast, that's talking about a rate of the area. So it sounds like we're looking for dA, dt. And what would the surface of this be? Well, if we're talking about having water filled up in a reservoir and emptying out, what is the surface that they're talking about? If I were to slice a cone, what would I form? Well, if I were to slice a cone and take a look at what I had, I would have a circle. And so it with a radius of r. Okay? Now, your radius when the height at this instant, if you remember, was when the height was 6. So the radius when the height is 6 is not going to be 3. The radius that they were talking about was the radius of the base, and that is not the same as this radius. So that's really important to recognize, okay? So we don't know what this radius is. All right, well, if I take a look at the formula for the area of a circle, because that's what I'm talking about, how fast is the area of this circle decreasing at this instant, because as the water goes down, that circle gets smaller and smaller and smaller in that cone. So the formula for area, of course, is pi r squared. Okay, well, let's look at everything that we have. All right, we have the height at that instant. We don't have the radius at that instant. And it would be a pretty difficult task to find that, okay? We also have dH dt. We don't know dr dt, which if I took the derivative of area with respect to radius, I would have to fill in a dr dt. So we have a lot of things that are related to height. So let's go back to this original ratio that we used and use that to replace the r so that we have our formula for area of this circle in terms of the height. All right, so if I do that, I have area equals pi times 3h over 10 squared. So that would be area equals 3 over 10 would be 9 over 100. So 9 over 100 pi, so I could actually do 9 pi over 100 and then h squared. Okay, so that is the formula that I have for area with respect to height. So now if I took the derivative of that with respect to time, all right, I would get dA dt, which is what I want, is equal to 9 100ths times 2 would be 18 over 100 pi, and then h dH dt. Okay, now if I look at that, I can work with this because I know what h is at that instant. It was 6, and I know dH dt. I just solved for that up at top. So I should be able to now put in everything that I'm looking for. Whoops. Okay, so let's see here. I have dA dt equals 18 over 100 pi, so I'm just going to stick that pi up there with the 18, times my height, which we know is 6 at that instant, times dH dt, which is that what I just solved for, negative 100 over 81 pi. Okay, so this now is what I need to simplify. Well, I noticed some things right away that are going to make this nice. Okay, I can cancel the pi's out. I can cancel the hundreds out. All right, so I have 18 times 6, which is going to be 108, 108 over, let's see here, just the 81 is all that's left, and a negative on the top. So my dA dt, which I know that can be simplified, but to save some time, we're just going to leave it, is negative 108 over 81 feet squared per minute. So that's the rate at which the area is changing. Okay, the last problem that we're going to look at tonight says that sand is falling from a chute, forms a conical pile whose height is always equal to 4/3 of the radius of the base. All right, so we would have a kind of a cone-shaped pile like this, all right, where the sand is kind of falling from the chute, if we had a chute up here, okay, and it's falling into this pile and it forms a cone shape. So you can kind of imagine that. All right, and it tells you here whose height is always equal to 4/3 of the radius. So that is telling you that that's giving you the ratio that we normally have to solve for. They just give you that directly. They're telling you that height is equal to 4/3 of r. Okay, so they're giving you that ratio without us having to solve for it at all. How fast is the volume changing? How fast tells you it's a derivative. Is the volume changing? So they want dV dt is what we need to find. When the radius of the base is 3 feet, so when r equals 3, and is increasing at a rate of 3 inches per minute. Okay, so it's increasing at a rate, and what is increasing? The radius is increasing at a rate of 3 inches per minute. Okay, and I just want to draw attention to something really quick. If we look, I hope you didn't miss it. It said the radius of the base was 3 feet, but yet the rate at which the radius is increasing is 3 inches per minute. And so we have feet here and inches here. So before we can go any further, we need to change that to have the same unit of measure. All right, so I have right now 3 inches in 1 minute. And what I want to do is convert that to feet per minute. So I need to convert inches to feet. So what I'm going to do is multiply by a factor. Sometimes it's really easy to do this, especially if they give you, if they had given me 3 feet and I needed to convert it to inches. Very easy, but sometimes it's harder for students to figure out how to go from inches to feet, okay? So, well, what we're going to do is take 3 inches and we're going to multiply by a factor of 1 that includes inches and feet. So if I put 1 foot over 12 inches, okay, what that does is it allows me to cancel out the inches, the unit of measure that I don't want, and what's left is 3 feet for every 12 minutes. Or that could simplify to 1/4 foot per minute. So 3 inches per minute is the same as saying 1/4 of a foot per minute. And that's my DRDT. Okay, so, all right, so now I have all this information. I've kind of unpacked everything that I know. And so I'm ready to go ahead and try and find the dVdt. All right, so I want to go ahead and grab the formula for volume. So volume is equal to 1/3 pi r squared h. All right, what I'd like you to do is pause the video and go ahead and work through plugging in everything that we have. First, you want to make sure that you get it in terms, this equation, in terms of just one variable. And since it's dr dt and r that we're given, we definitely want to get it in terms of r. So use this and replace the h, all right, and then go ahead and take the derivative with respect to time, plug everything in and see if we get the right answer. Okay, so go ahead and pause now, and I'll come back in a minute. Okay, so let's take a look at what I came up with, and hopefully it matches what you came up with. So if you look here, we went ahead and I took my volume formula. I went and replaced the height with the 4/3 r. I cleaned that up and made that 4/9 pi r cubed. Then I took derivative of that with respect to time. So that gave me this equation, dV/dt equals, I multiplied 4/9 times 3 and got 12/9 pi r squared, and then dr/dt. Then I plugged in what I knew. So I don't know dV/dt, that's what I'm solving for. So equals, I simplified 12/9 to 4/3, copied the pi, the radius was 3 squared, and then times dr/dt, remember we found to be 1 foot per minute, 1/4 foot per minute. And so then I was able to do a lot of canceling here, right? The 3 canceled into one of my 3 squareds, the 4's canceled, and so all that was left was 3 and pi. And then notice, please, that you should have your unit of measure for volume. The rate at which volume is changing should be foot cubed per minute. Okay, that wraps up our lesson on related rates, specifically with cone-shaped problems and the volume of cones. I hope that you took great notes and especially took note of the difference between these problems and the other ones where both the radius and the height were changing, and so in order to use our formula we had to use r in terms of h or h in terms of r. So I will see you next class, and we will make sure to be practicing some more of these. Have a good night.